So the last time we left off, we were talking about refraction. Okay, and the refraction is the changing of the wave characteristics, or the changing of the direction of propagation of waves when it enters into a different medium. Okay, and we characterize those mediums in terms of their densities. Okay, so in the deep area, the water density is different than in the shallow area. Okay, but I think the biggest takeaway that you should have is that in the deep area, the wavelength of the wave is much bigger, okay, compared to the shallow area. Okay, the wavelength changes and the wave speed changes as well. Okay, so both this one, the wavelength and the wave speed. Okay, if the wavelength is bigger, the wave speed is bigger. If the wavelength is smaller, the wave speed will be smaller. The single most important thing that we need to remember is that the frequency is unchanged. Okay, very important thing. The frequency remains unchanged. Um, yeah, and of course, the direction of propagation also changes. Okay, and we talked about the two types of changing of direction. Either it is the change of direction is the wave is bent towards the normal, or it is bent away from the normal. Okay, and we did this example the other day lah. Okay, and it's important to note now that when we talk about towards the normal, away from the normal, means we're talking about the angle, okay, between the wave and the normal line. Okay, so I hope that the other day the exercise that you did now will remind you that the normal line is always 90 degrees to the place, the sempadan lah, okay, where it is going to refract. Okay, so if it is saying it like this, then the 90 degrees also will be saying it. If it is straight like this, it is still perpendicular, but it is the same line as this. That's why it doesn't refract here. Okay, it only changes wave speed, but it doesn't change direction. Okay, so these two words, sorry, I marked the angle wrongly. The angle should be here. Okay, so these two words are very important. Okay, refracting towards the normal and refracting away from the normal. Okay, are the ways we use to describe the change in direction. Okay, change in direction after refraction occurs. Okay, so it's either we change it towards the normal or away from the normal, further from the normal, okay, as we saw in the other day. Now, I also mentioned in the previous class, okay, that actually when waves refract, okay, they kind of take the shape, okay, of, let's say, for example, the coastline, okay, the tepi pantai lah kan, okay, they also kind of take the shape of the thing that the surface that they are refracting from. Okay, so for example, if you have a straight wave coming towards a place where it is, it is bent like this lah. It looks like a lens. I know it looks like a lens, but we're not talking about lens yet lah. Let's say the shape of the shore is like this. Okay, so what we're going to find now is after refraction occurs, it's going to take this shape. Okay, it's going to take this shape and it's going to be as if it's going to be focused to one spot lah. Okay, and then after that it will, it will continue to spread out. Okay, likewise with this. So this one we can assume. Take a look at this. The top one, it takes the shape of the place where they are crashing into. Okay, so this one, it's going to be shaped like this, and after that, it's going to shape like this lah. Okay, it's going to go away. It's going to spread out. Okay, this one is focus. Okay, this one is going to be spread out. Okay, and so we find that it takes the shape of the place. It takes the shape of the line lah. Okay, where the border is. Okay, so we look at because that's the first thing that they encounter. If the first thing they encounter is on like keluar macam ni bahkan, so the shape of the wave will be keluar and it will be focused inwards. Where else kalau dia termasuk macam ini, okay, it's going to take this shape and it's going to be spread outwards. Now this one is more obvious in light waves lah. Okay, when we talk about light waves, then this becomes a little bit much more easier to follow. But the principle is the same. Actually, if we use water waves to do this, we will see this effect. Okay, where if you have this shape, then it will show go in, and if you have this shape, then it will like kind of like spread out. Okay, not so important for this chapter. Okay, but it's good for us to know lah, because when we want to talk about, I mean, if you remember in the Monday's class, I said, why is it that our coastline, okay, kita punya tepi pantai itu kan dia berubah-ubah? Why does the shape change? Okay, it has something to do with refraction. Okay, which we'll talk about in a little while. First, let us do a little bit of calculation questions. Okay, so take out your calculators and whatever that you want to use to calculate, and let's do this together. Okay, and when I say do together, means we do, and then after that I call somebody. Okay, so please don't fall asleep on the wheel. Okay. Again, the single most important thing when we are doing calculation questions involving refraction is that the frequency before refraction and the frequency after refraction is the same. Okay, so plane wave has a wavelength of 2 cm and a velocity of 8. Okay, as it moves over the surface of shallow water. Okay, so in shallow, okay, the velocity is 8, the wavelength is 2. Okay, let's label this correctly. Now, when it moves into an area of greater depth, okay, so we are going into deep area, the velocity is going to become 12. What is the wavelength of the wave? Okay, so we hold on to the fact that the frequency of the shallow equals to the frequency of the deep. Okay, taking into account the formula V equals to F lambda. So therefore, if I bring the lambda across, V over lambda equals to F. So that means the velocity of the shallow over the lambda of the shallow equals to the velocity of the deep over the lambda of the deep. Okay, and this is what we want to count, the lambda of the deep. Okay, can you calculate that now, please? Substitute in, calculate it now. I'll give you 1 minute, and then I'm going to call somebody.
3
3 what?
cm.
Okay, I think it should be 3 cm lah. Okay, good. All right, so it's 3 cm over here. So the calculation is not really that much. Okay, we just have to remember the wave equation, okay, which is V equals to F lambda. And of course, we have to remember that in the shallow and in the deep, oh, it sounds like a sound. Okay, in the shallow and in the deep, okay, the frequency remains the same. Okay, nothing, everything else will change, but the frequency remains the same. And this still follows our hypothesis. Okay, we said that the bigger the depth, the bigger the wavelength. Okay, so the depth is the bigger the depth. Yes, the bigger the depth, the bigger the speed, and the bigger the wavelength. So the speed is bigger, the wavelength also is bigger. And 3 is bigger than 2. 12 is bigger than 8. Okay, very important. All right, same thing. Okay, except that now they don't give the wavelength. Okay, so first of all, I want you to take a look at these two diagrams and tell me what the wavelength in P and what the wavelength in Q is. Okay, this one first. Okay, do you remember how to calculate the wavelength? Wavelength is from one line to another. Okay, but this is a combination of a few lines. So yeah, so be very careful. Okay. All right. Let's have Vion. Okay, Vion and Trevor. Can you please, Vion, can you tell me what is the wavelength in P? And Trevor, tell me what is the wavelength in Q?
cm.
Okay, so, oh, sorry, 3 cm, all right. How do you get 3 cm? Can you explain to us?
12 divided by 4.
12 divided by 4. Why 4? So bad, I keep asking this. Yeah. Why 4?
The wavelength got 4.
Okay. All right, so this is one wavelength, Bakan. Okay, thanks, Vian. Okay, so 1, 2, 3, 4. Covers all 12. So 12 divided by 4, you'll get 3. Okay, Trevor, Q, please.
1.5.
Okay, 1.5 cm. Simply because there's 1, 2, 3, 4, 5, 6, 7, 8. Wow. Okay, so 12 divided by 8, you'll get 1.5. Okay, same formula again. Okay, if they say now calculate the speed of the wave in Q, that means you want to find the VQ. If the speed of the water wave in P is 18, okay, so VP equals to 18. Okay, take some time to calculate this. Same formula as just now. Okay, V over lambda equals to V over lambda equals to V over lambda. 9 cm per second. Okay, yeah, I think it should be correct. 9 cm per second. Okay, so again now guys, the good thing about this formula, okay, the good thing about this formula is because it is a ratio, okay, you just have to make sure that the units are the same. It doesn't have to be an SI unit. Okay, can I change the 18 centimeters per second to 0.18 meters per second? Because meters per second is a standard, right? You can do that if you want to, but it is unnecessary. Okay, because if one is in centimeters per second, you just make sure that the other one at the end is ending at centimeters per second. Okay, so that's the good thing about ratio formulas. Okay, you just have to make sure that the units are the same. All right, let's do number 3. Okay, diagram shows a water wave moves from region P to region Q at different depth. Which region is the shallow region? Why? Okay, Rahman, why don't you help us out? Which region is the shallow region and why? Why? Why Q? Okay, Q is correct. Why Q? How you know it's a shallow region?
Because the wavelength is more.
Okay, very good. Because the wavelength is smaller. That's an indication to us, okay, that the region is shallow. All right, great. Okay, let's compare the speed and compare the frequency. Can I have Ivers for the speed and Ari for the frequency? Compare, very easy one. P and Q, so the speed of P, what speed of Q, or the frequency of P, what the frequency of Q. The frequency of the region is greater. It's okay, Ari. The frequency of region Q is greater than P. Really? Q has a bigger frequency. P has a less frequency. Astaga. Is that true? What did I say about frequency when refraction happens? Remember? The frequency actually is the same. Okay, that's why we have this formula. That's why we have this formula. Frequency never changes. Okay, the frequency changes and we cannot calculate anything already. Okay, so it's very, very dangerous now. So the frequency of Q is equals to the frequency in P. Okay, now back to the speed of waves.
Water waves in region Q is the speed of water waves in region Q is higher than region P.
Speed in Q is higher than speed in P. Is that true? What do the rest of you think? We established the fact that Q is the shallow region, okay, because the wavelength is smaller. So is this true? In the shallow region, the speed is bigger than the speed in the deep. Okay, actually it is the speed in P is higher than the speed in Q. I like the way that you answer, Bernardine. The full answer, the sentence is correct, except that the comparison is wrong. Okay, so this is where we learn. The frequencies are equal, but the speed is different. It doesn't mean that the wavelength is smaller, means it is faster. This is something that is countercultural. Kan? We always think that, oh, since the wavelengths are so far apart, means it's slower. Actually, it's not. Okay, it is precisely because the wavelengths are far apart that they are faster. Okay, so the speed in P is bigger than the speed in Q. Remember the ticker timer? Remember the ticker tape experiment in chapter 2? You have this tape and then you have these dots over here, right? Okay, so if you have a car, the other day I said during revision, it's like a car that has a leak on it. Ada lubang lah di dalam dia punya tong gas bahkan. So if the dots are very near, okay, and in the dots are very far apart, okay, what do they tell us? The dots that are very near tells us that the car is moving slowly. The dots that are very far apart, it tells us that the speed or the velocity of the car is high. Likewise, in the wave also is the same. Since the waves are far apart, the wavelengths are far apart, the speed there is faster because the frequency is the same. Okay, the thicker tape and this wave thing is the exact same situation. The bigger your wavelengths are, the bigger your speed. The bigger your distances between the two dots are, the faster your car is going. Okay, so let's learn to adjust our our thinking. All right. Now diagram shows a stair shaped tank. This one the answer is already given lah, no choice. Three regions X, Y, Z. So X is here, Y is here, Z is here with their respective increasing depths. So the depths are increasing. So we're supposed to draw a diagram to show the refraction of waves lah. So obviously X will have a smaller wavelength, and then Y will have slightly bigger. Okay, and then Z will be much bigger. Okay, so small wavelength. This will be X, this will be Y, this will be Z, which is kind of like this lah. Okay, although, okay, sorry, it goes from Z to X pull up. Sorry. So this is correct because the vibrator is here. So it goes from Z to X. Z is deep, X is shallow. Okay, so big wavelength to small wavelength. Again, these exercises are meant to help you to see that when the depth is big, the wavelength is big, and the wave speed is big. It all comes together. Okay, the three of these come together. All right, let's look at a little bit of application, okay, of our refraction in daily life. Okay, so the first thing that we open this subtopic with is to talk about the seawater wavefront. Okay, why is it that our coastline is not like one straight line, but actually there is a shape to it. Okay, so on the coastline, there are two very common regions. Number one is this region called the Cape. So, yang keluar macam ni bahkan. Okay, so we call this the Cape. Yang ada keluar macam ni, this is a very small Cape lah, but this is a much bigger Cape. Okay, yang dalam bahasa Melayu kita panggil sebagai Tanjung. Okay, which is very similar to ours lah, Tanjung Aru. Okay, nowadays Tanjung Aru is a lot like this, but there is one section at Tanjung Aru where it really protrudes out like that. Dia macam memang terkeluar. That is the actual Tanjung lah. The rest of it is just seashore that is not really Tanjung. Okay, but Tanjung Aru is an example of a place where there is a Tanjung, and we call this a cape in English. Okay, now the opposite of the cape, okay, kalau cape dia adalah keluar bahkan, yang masuk macam ni, the part where it goes in like this is called a bay. Dalam bahasa Melayu, bay is called teluk, like Teluk Likas. Okay, so the Teluk Likas is a very big bay lah. Actually, there's a very tiny bit of capes in there, but the majority of Teluk Likas is one big bay. Okay, so this diagram is a very compressed diagram. Actually, the area of the cape is very big, and the area of the bay is even bigger, much bigger area of bay actually. Okay, but refraction, the refraction of water waves over time, okay, the refraction of water waves over time causes the cape and the bay to take shape. And when I say over time, I'm not saying over 2 months or over your lifetime. It's over hundreds and hundreds of years, millions, thousands of years, okay, in order to form that shape. So the reason why we're able to enjoy ourselves in Tanjung Aru and in Teluk Likas today is because of something that happened way before you and I were born. Okay, it started way back then. Okay, and that's why we're able to, kita boleh enjoy di Tanjung Aru dan di Teluk Likas. Okay, because of the refraction of waves over this long period of time. So, why does the waves become closer to one another and follow the shape of the shoreline when they are approaching the beach? This is the one thing. Now, when we talk about closer to one another, we're talking about the wavelength becoming smaller. So why does the wavelength become smaller? Okay, it is because the water waves are traveling from the deep to the shallow region. Point number one. Point number two, the speed of the water wave decreases. Okay, and we know that when the speed of the water wave decreases, the wavelength also decreases. That's why the waves become nearer and nearer to one another. Okay, so this one we need to follow that logical sequence lah. It's going from deep to shallow, so the speed decreases, the wavelength decreases, and the water wave refracts towards the normal line. Okay, this is a very, very important thing. It refracts towards the normal line. Okay, this way. Okay, no matter which part of the wave you are, it's always going to refract towards the normal line. Okay, because it is going from deep to shallow. Okay, if you remember in the drawing that you did 2 days ago, now, oh sorry, Allah. Okay, when it is going from deep to shallow, okay, we established this, right? We said that the wave is going, is refracted towards the normal line. Okay, so there's now no such thing as cape is towards the normal line and then bay is away from no. Everything, because we're going from deep to shallow, okay, deep water region high speed, shallow water region low speed, okay, so it is always going to refract towards the normal line. Okay, now the other question is, why is it that the water at the cape has a high wave? Why is it that the waves are higher in the cape? You know, when you stand at the bay, okay, when you stand at the bay, like, you know, the Likas, okay, you stand at the seashore, it's like la 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 la, the wave is just coming in normally. But if you stand at the cape, especially during rainy season, okay, you'll find that the wave speeds are very high. Okay, why? Okay, if you take a look at how the waves are refracted, look at this cape now. You have this wave coming in this way, refracted towards the normal like this, and this wave also coming in this way, refracted towards the normal. So you have like kind of like a convergence of waves. All the wave itu kan macam tertumpu kepada satu tempat. Okay, so more energy is converged di sini. Okay, more energy is converged. Dalam bahasa Melayu, converge is menumpu. Okay, terfokus. Okay, more, all the energy of the wave is focused at the cape area. Okay, so the water at the my goodness, the water at the cape area has a high amplitude. Although they are slow, I'm not saying that you know they are moving very fast. They are slower than at the deeper regions. Okay, but because the energy is, you know, focused at one point, so at the cape, okay, is where the energy is highest, okay, for the waterway. So this is an example. Okay, so nobody nobody in their right mind will build a house on a cape. Okay, unless you want to forever be fixing your house lah. What we do build, okay, on capes are lighthouses. Okay, back last time sebelum ada things like GPS and everything, right? If there are ships coming, kalau ada kapal yang mau berlabuh kan, okay, they will have to put a lighthouse over here and they have to turn on the lighthouse to warn the ships. Let's say if a ship is coming here okay, and you can't really see in the dark, wondering, which part is the cape, which part is the bay, because you definitely don't want to park your ship at the cape. Okay, that is just nonsense lah kan. Who wants to park the ship at the cape? Okay, so they want to park their ships, you know, at the bay where the port usually is. So nobody builds a port, okay, at the cape area. But people build lighthouses, and the lighthouse is a tall structure. Dalam bahasa Melayu dipanggil apa? Rumah api kan? Ya, rumah api kan. So the lighthouse is usually a tall, almost cylindrical structure, and then up here there is a light that they're pusing lah. Okay, to tell the ships that, hey guys, where I am now is the cape. Don't come near me. Okay, otherwise your kapal will be destroyed. Okay, so we build lighthouses on cape areas because of the energy convergence there lah. Okay, question C, why is the water bay calm? It's the exact opposite of this. If B, more energy is converged at the cape area, water has high amplitude. In the bay, okay, the energy of the water wave spreads to a wider area. Okay, we come back to this. Okay, take a look at this. If we just take a look at these two, okay, we see that the energy is spread out. in the cape, the energy is focused in. Okay, although it's the same line, okay, although it's the same line, but depending on the situation and the area where they're in, okay, the bay, okay, the energy spreads out, okay, to a wider area, and because of that, the amplitude of the water wave is low, and so the water at the bay is calm. Okay? And usually, in island structures, okay, we find that Cape Bay, Cape Bay, Cape Bay, usually they are berselang-seli. Okay, for example, in this picture over here, this is the bay, this is a cape, sorry, this is the cape. Okay, so it's, cape is usually where we have a lot of rocks, okay, and this whole section over here is the bay. So you can imagine that all the waves they come in, they are focused over here and they are spread out over here. See this wave and this wave, it's kind of spread out. So the amplitude of the water wave is low. the height of the water wave is low because the energy is lower, and because all the energy is spread out. Okay. One very important thing to remember is that the energy of the wave, okay, the energy of the wave contributes to the amplitude of wave. If the wave has high energy, okay, it's going to be, very high amplitude lah. Okay, you're going to get, just to recap, amplitude is this lah. Okay, dia punya ketinggian ombak itu. Okay, so if the energy of the wave is low, okay, then you will have a smaller amplitude. Okay, so a lot of things to consider when we talk about waves. Okay, is the wave fast? Is the wave speed fast? Sorry, is the wave speed bigger? What about the wavelength? Is it a longer or shorter wavelength? And these two, they're saling berkait rapat. Okay, the bigger the wavelength, the bigger the wave speed. But it is possible for something to have a bigger wavelength and a bigger wave speed to have a small energy. We always tend to think that, bigger wavelength means bigger energy. Not necessarily true. Okay, not necessarily true. It's possible. It is possible. Okay, something with very big wavelength and very high speed to have small amount of energy. Okay, dia punya amplitude depends on how it is refracted lah. Okay, so the refraction causes the change, not just in wavelength, not just in wave speed, but also in the amplitude of the wave. Okay, where it is meeting, where the waves converge, where they are focused, the energy becomes bigger. So they bergabung. But when it is spread out, all the energy macam kena sapu lah, kena sebar semua sama rata. So the amplitude of the bay is calm. All right, I think this is a video. This next few ones are videos. So.
Okay, one of the things we're going to be doing in lab is looking at what's called refraction, which is the bending of waves and their changing direction as they come into shallow water near shore. You may know that as waves move toward the shore, they create an orbital motion in the water, and that orbital motion dies out to nothing at a depth that we call the wave base, and that depth is equal to 1/2 of the wavelength of the wave. And so when waves come into water shallower than their wave base, they begin to feel the bottom. That orbital motion brushes against the bottom, and the waves begin to slow down. And that causes the waves to slow down and bend and change direction, which is the essence of refraction. For example, in this animation, you can see the waves in deep water are approaching straight, but they're going to slow down in the shallow water near the headland here, but still go fast in the deep water and the bays on both sides. And that causes the waves to bend and wrap and conform somewhat to the shoreline. That's what refraction is. And one of the things that's interesting about refraction is it's responsible for creating a lot of the famous surfing breaks that we see in Southern California and elsewhere. For example, this is Rincon Point up near Ventura, and the swells are approaching here straight from the Pacific Ocean, but they're slowing down in the shallow water near the point, but still going fast in the deep water out here, and that causes the waves to bend around. So by the time they reach here, you can see the waves changed its direction by about 90 degrees. So that's extreme refraction, and it creates a tremendous right break. It's a famous surf spot at Rincon. Here's another example. These two little islands out near Hawaii, the waves are coming in from up here, and they're approaching the islands, and I've drawn the wave crests so you can see them a little bit better. And look at what happens. As these straight waves approach the islands, they slow down and drag in the shallow water near the islands, but they're still going fast in the deep channels away from the islands. And so they change from straight to rather radically bent. That's refraction. One of the things you'll be doing in lab is drawing what are called refraction diagrams, which is your prediction of how waves will bend and change direction as they come into different shapes of coastline. And so it's like you're up in an airplane and we give you the starting waves here in deep water, and your job is to draw the wave crests showing how you think they're going to bend and refract as they approach the shallow water. You're always going to show them slowing down the closer you are to land where the water's shallower, but going faster where the water's deeper. Probably the easiest rule to remember is the waves tend to conform to the shape of the coastline, not completely, but they tend to wrap to the shape of the coastline. Well, one of the interesting things about, oh, by the way, this picture here is a pretty good model to see where the land bulges out like this. That looks a lot like ring knot, doesn't it? So you can see it happens in real life right there. Okay, one of the neat things about refraction is that it can cause waves to bend their energy into one spot to make particularly large waves. And a lot of famous surfing waves are created this way. If a wave approaches the land straight, like the hand here, its energy is going to be spread out evenly across the coast. But if refraction causes the wave to bend concave in the direction that it's traveling, like the curved hand here, it's going to cause it to focus its energy into one spot, and that's going to tend to make a really big wave in just one spot. This is shown in this diagram here, where you can see an underwater ridge. These contour lines show an underwater ridge, so it's shallower water here and deeper water here and here. And as these swells approach, they're going to slow down over that ridge, but go faster over here. And that's going to tend to focus the energy right over the ridge and create a big wave right there where that X is. And this is the kind of situation we see at a lot of famous surfing spots. For example, this spot, some of you may recognize if you know about surfing waves, is Jaws or Piahi in North Shore of Maui. And a very large wave forms here just in one spot during certain northwest swells. It's a classic what's called an A-frame, where the wave just pops up in the center and is low on both sides. So it's kind of like the letter A. And the reason for that is that the waves wrap to an underwater, oh yeah, here's Laird Hamilton on the Jaws, on the Piahi wave. The waves wrap to an underwater ridge. It's shallow out here in this area, but it's deep over to the sides. And that means the waves start out straight, but they get more and more bent, more and more concave. And that focuses their energy into the spot right over the ridge, giving you both a left and a right break right over that ridge. Well, the wave you're going to be looking at is Mavericks in Northern California. And you're going to be trying to figure out why there's a big surfing wave that forms at one particular spot at Mavericks. Because again, you can see it's a lot like the Piahi wave. It's kind of an A-frame with just a big wave right in one spot. So on a big day at Mavericks, there's a reason why the waves form there, and you're going to figure out why. It has everything to do with refraction.
Okay, so yeah, there's a little bit of a more detailed explanation about why waves, form, especially big waves lah. Okay, we always tend to think that the waves only form just because of what's happening on what we can see, okay, on the surface. But actually, if you listened to this guy just now, you notice that actually there's always this thing called the Undersea Ridge. Yeah? This is like over the years, over many years. Okay, so the rock formations have formed these ridges that that take this kind of shape. Okay, so it's like kind of a bend shape like this. So the bigger the Undersea Ridge, or the further apart the Undersea Ridge, the wave is going to start accumulating or start focusing much earlier on. Okay, and that's why you get all these shapes of the waves that's like this. It's pretty interesting that only this side yang dia punya wave sangat tinggi, the rest all is just like tala macam tiada saja. Okay, because it just tells you that the wave has been refracted towards the normal, okay, and is focused on that particular part in the ridge Okay, a little advertisement about people riding waves. Unfortunately, maybe in Malaysia we don't really have that much high of a wave. We do but I think because relatively our land is still pretty young, and the ridges are not so big. That's why we don't really get that much big of a wave compared to places like that was in the example just now is, I think one of the examples is in Hawaii, okay, which is pretty pretty old in that sense. So you get much bigger waves over there. There are big waves here in Malaysia, like, okay, for example, in Sabah, it'll be on the east coast lah. Okay, places like Sampurna. No, not even Sampurna. No, not Sampurna. That's for diving. Maybe like, okay, places like in Kudat lah. Okay, I know Kudat definitely has, because there's these two huge capes over there. So places like in Kudat and Pitas will probably have much bigger waves compared to the ones that we see here in KK, which is like the ultimate sadness lah. Don't have like, KK is one huge cape. One huge bay. So not so suitable lah. Okay, in West Malaysia, it's more on the east coast also. So places like Terengganu, Kelantan, Pahang, okay, they will have much bigger waves over there lah, because they're facing the main sea lah, obviously lah. Okay, places like Melaka, Johor, Perak, all face the Straits of Malacca yang kena halang oleh Sumatra, so it's like not really that much of a wave. Okay, but again, the formation of waves, okay, the formation of waves, the size of the waves are all applications of refraction. But now we come to another one, which is sound waves. Okay, we want to talk about sound waves in the day when it is hotter and in the night when it is colder. Okay, and this is a very important thing for us to remember. The speed of sound waves in the warm air and cold air. And this is an interesting one. The speed of sound in warm air is greater. Okay, because the temperature in the warm air is greater, so the air molecules gain more kinetic energy and move faster. Okay, let's think about this logically. So, of course, this is normal. Okay, there is more energy in the air molecules, so they move faster. So, high speed. Okay, and what did we say about high speed and wavelength? The wavelength was, high speed means high wavelength. Okay, this one. Okay, and so why is it that we cannot hear, if let's say somebody is shouting on the other side, it is harder for us to hear that sound in the daytime than in the nighttime. Okay, and this is something that I realized, especially coming here. I realized that when people sing karaoke, for example, if you have a wedding next door or something, right? Okay, you find that the sound is much louder at night compared to the daytime. Like, okay, like time kawin or if there's an event at the stadium wow, feels like so long, bro. Okay, if it's an event at the stadium, in the daytime, we don't hear it so much, but at night, we can hear it from very far away. Okay, pretty interesting. Okay, so why? Number one, sound waves travel faster in warm air. We established this just now. Okay, because the air molecules, have more energy, so they can carry the waves much faster. Okay, secondly, on a hot day, the layer of air near to the surface is warmer. Okay, so this is a hot day. So warm air is less dense. Okay, so sound travels from hot to cold air. The speed of the sound decreases. So think of this as the warm air is the deep region. Okay, the cool air is the shallow region. Deep go to shallow means it's going to be refracted towards the normal line. Okay, remember it this way. Warm air is the deep region in water. Cool air, okay, when the air is cooler, is shallow region. Shallow region means what? Smaller wavelength, smaller wave speed. Okay, and as sound travels from deep to shallow, it's going to be refracted towards the normal line. Okay, and because it is refracting towards the normal line, it is going to be refracted away from the earth. So, the loud sound that comes out, although you're here, because the sound is refracted, it's going to be refracted away from you. So yes, you can hear it, but you can't hear it so clearly. As opposed to at night. At night is entirely terbalik. From all these five kita kasih terbalik saja. Sound waves travel slower in the cool air. On a cool day, the layer of air near the surface is cooler. Kan di bawah sini cooler. Remember, cold air is shallow bahkan. Sound travels from hot to cold air. So sound travels from hot to cold air. So the speed of sound increases. Okay, let's take a look at this. At night, the ground cools. Air layer near the ground is colder. Sound travels from cold to hot air. Cold to hot air. So the speed of sound increases. Why is it that sound travels from cold to hot air? Because down here is cold. Okay, it's trying to travel towards the hot air. So dia mau naik di sini bahkan. Tapi because the speed of the sound increases, the sound is refracted away from the normal line. Okay, and it is moving towards the earth. So in the daytime, the sound goes upwards, away from the earth. So you can't really hear it very clearly. But at night, bila orang berkaraoke pada tengah malam, okay, you can definitely hear it better, although you're very far away. Because sound waves move towards the earth, it travels from cold to hot air, and it increases in speed, Speed increases, it's going to come to us much faster. Okay, it's going to be refracted. Okay, so the next time when somebody singing karaoke at night, okay, like maybe 2 blocks away from your house, and you're wondering how come I can hear the sound at night, but in the daytime I can't really hear. It is because of refraction. Okay, refraction of sound. Okay, let's last 2 videos and then we'll call it a day.
In 479 BC, when Persian soldiers besieged the Greek city of Potidaea, the tide retreated much farther than usual, leaving a convenient invasion route. But this wasn't a stroke of luck. Before they had crossed halfway, the water returned in a wave higher than anyone had ever seen, drowning the attackers. The Potidaeans believed they had been saved by the wrath of Poseidon. But what really saved them was likely the same phenomenon that has destroyed countless others, a tsunami. Although tsunamis are commonly known as tidal waves, they're actually unrelated to the tidal activity caused by the gravitational forces of the sun and moon. In many ways, tsunamis are just larger versions of regular waves. They have a trough and a crest, and consist not of moving water, but the movement of energy through water. The difference is in where this energy comes from. For normal ocean waves, it comes from wind. Because this only affects the surface, the waves are limited in size and speed. But tsunamis are caused by energy originating underwater, from a volcanic eruption, a submarine landslide, or most commonly, an earthquake on the ocean floor, caused when the tectonic plates of the Earth's surface slip, releasing a massive amount of energy into the water. This energy travels up to the surface, displacing water and raising it above the normal sea level. But gravity pulls it back down, which makes the energy ripple outwards horizontally. Thus, the tsunami is born, moving at over 500 miles per hour. When it's far from shore, a tsunami can be barely detectable, since it moves through the entire depth of the water. But when it reaches shallow water, something called wave shoaling occurs. Because there is less water to move through, this still massive amount of energy is compressed. The wave's speed slows down while its height rises to as much as 100 feet. The word tsunami, Japanese for harbor wave, comes from the fact that it only seems to appear near the coast. If the trough of a tsunami reaches shore first, the water will withdraw farther than normal before the wave hits, which can be misleadingly dangerous. A tsunami will not only drown people near the coast, but level buildings and trees for a mile inland or more, especially in low-lying areas. As if that weren't enough, the water then retreats, dragging with it the newly created debris and anything or anyone unfortunate enough to be caught in its path. The 2004 Indian Ocean tsunami was one of the deadliest natural disasters in history, killing over 200,000 people throughout South Asia. So how can we protect ourselves against this destructive force of nature? People in some areas have attempted to stop tsunamis with seawalls, floodgates, and channels to divert the water. But these are not always effective. In 2011, a tsunami surpassed the flood wall protecting Japan's Fukushima power plant, causing a nuclear disaster in addition to claiming over 18,000 lives. Many scientists and policymakers are instead focusing on early detection, monitoring underwater pressure and seismic activity, and establishing global communication networks for quickly distributing alerts. When nature is too powerful to stop, the safest course is to get out of its way.
Okay, one last one. Tsunami. Quake under the sea. But also, as the wave moves towards the shore, Okay, you saw what is known as the wave shoaling. Okay, because there's less land for it to move in. Okay, so it's going to gather all this amount of energy towards you. And really, there's nothing much that you can do to stop it. Okay, I think that last line in the video before this is quite interesting lah. Okay, the fact that when nature becomes unstoppable, then the best thing to do is to run away from it lah. Okay, sometimes let nature take its course. Ultimately, we are also a part of nature. All right, so for your homework, the same thing, the entire tutorial 5.4, but there are some questions that I think that you don't have to answer. I will list them down later for you in our group, and I will write them down. Sorry, I will tell you how to write the answer down. Okay, but it's pretty much like last week. Okay, the objective questions first, then the subjective questions and the essay questions in one PDF file.